Okay, everybody, let's get started. You're, of course, back in system software. Last time we looked at type checking in a little bit more general than what you're actually going to have to do for your project. But I think it's good to go through this type checking algorithm just to understand how your compiler uses types and how even interpreted languages use types to ensure the safety of your running program. So just a little quick review of types from last time. You can kind of think of it like a proof that your program won't have certain runtime errors, certain classes of runtime errors, these untrapped errors, like adding a floating point representation of a number to an integer representation of a number. So does anybody have questions about type checking? Oh, yeah. Is that what you mean? Okay, yeah. Night mode. Okay, anybody have questions about types, what we went over last time? We ended right at the end of walking through type checking, an example of our Simple C program. Everybody gets types? Everybody gets type checking? More or less?
More or less.
Okay.
Sort of, kind of.
Sort of, kind of. Okay. So you'll only have to do very basic type checking, just making sure that the symbols have been declared before they're used and they're not multiply defined. Once we get to adding functions, then we'll have to do a little bit more type checking, and that we'll have to make sure all of the arguments are provided to a function. Okay, so this is the last lecture in talking about variables. So your project is due, what, in a week? Is that right? Or is it Tuesday?
It's like
Let's see.
30th. Yeah, we have a full week and then
30th?
It's like 2 Tuesdays from now.
This is saying
29. Yeah, that's 2 Tuesdays.
2 Tuesdays. Okay, so you still have quite a bit, almost 2 weeks on your project too. Okay, so today we're going to go over how to do code generation for variables. So there's actually not that much you have to do in order to implement variables. I mean, the pieces will take a lot of coding, but conceptually, there's only a few additional constructs that we have in our language. So if we look at our new language, so who can tell me again what the new constructs are for variables in this language? What did you say? The read is new. So we have a way to read in a variable from input, from standard in. What else? Assign. We've got an assignment statement. Anything else? What's that? I'm sorry, say again? You mean in factor? I mean in expression? Yeah, so expressions can now be an identifier, which is a variable name. Anything else? Is that it? Declarations, yeah, so we can declare variables. And we saw that we can have a program that looks like, well, I have the example here. A program that looks like this, where we can now declare variables, kind of like we do in C. We can read them from standard input, and then we can assign them and use them in expressions. Okay, so any questions on the language definition at all? Yeah.
So let's say we have something where would it be possible to have something like, say, int x equals 3, print negative x?
No, for a couple of reasons. So if you said int x equals something, this grammar doesn't define any syntax that allows that in the input. So there's no case where you have int identifier followed by an equal sign. So in C, you can think of this as syntactic sugar for doing a declaration followed immediately by an assignment.
So whenever we will have a declared variable or anything, is it possible that we'll be dealing with negative variable names?
Oh, okay. So this is something that people asked on Piazza as well. So if we look at the expression grammar here, would that parse? Would I be able to parse print minus sign identifier using this grammar? Who says yes? Who thinks we can parse that here? Who thinks we can't parse it with this grammar? So what's going to happen if we try to parse this? Well, we have print followed by an expression. So somewhere in expression, we have to be able to begin with a minus sign. But there isn't even any construct here that begins with a minus sign. Or, is a minus sign followed by an epsilon production. Expression cannot be epsilon, can't be the empty string. And there's no other terminals that begin with minus. So there's no way in this grammar to have negative identifier. And so there's a very kind of fine but important distinction here between different kinds of operations that the same symbol represents. So the minus sign in arithmetic is highly overloaded. It can mean a negative number. So in numbers, the lexical specification for numbers allows a minus sign to be part of the token, the number token, which means a negative number. We can have a minus sign between two expressions, which is the binary operation. Binary operation just meaning it takes two operands. And this is the infix version of that binary operation. The operation that your classmate is asking about is the unary minus operation. And the meaning of this is to take whatever the value of that operand is and basically multiply it by -1. So these are all typically use the same symbol, even in modern programming languages use the same symbol for this, but they actually are different operations, and the compiler will represent them differently at the machine code level. So if we have a number that has a minus sign before it, that will be represented in like 2's complement as a negative number in the representation. If we have a binary minus subtraction operation, that will be the subtraction operation at the machine code level. And if we have a unary minus sign, depending on whether the architecture has that, if the architecture has a unary negation, then it'll use that. Otherwise, it'll just multiply by -1, use multiplication for that. So that's a good question, and somebody brought this up on Piazza as well. But I wanted to keep this language simple. You can always, because of the rules of arithmetic and the rules of algebra, you can always just multiply by -1 if you want to do negation. Oh, but that's a good question. Any other questions about the language definition? It's all pretty much clear to everybody? So the language is a fairly small extension to last time, to Project 1. The main complexity in Project 1 was of course, doing all of this recursive stuff. But, okay, yeah, question?
What does read do?
Oh, read? Read takes a number from standard input. And so I've given you a function in the new template. So watch the last lecture if you need, if you want to learn about the new template and how to use it. I've given a header file that'll make it easy to use this template. What read does is it takes a number from the input in ASCII code, an ASCII coded number as input from the standard input, and takes one at a time on one per line, and it returns an integer. So this is what your read statement will translate to in LLVM. It'll be a read from input, and then of course a store, which we'll go over today, a store of this value that's in T1 to the variable's memory location. But read is just saying read this value from input. It's like print. Print prints whatever that number is to standard output on a single line. Read reads whatever is in the standard input, one number per line, and brings it into and returns that number from the read integer method. So if we look at the definition of read integer, I just compiled this from using, what did I use? Can't remember what I used now. Scanf or something? Or, I don't remember what I used. But yeah, it should be in here. Oh yeah, scanf. I use scanf for this, and I just use, I use scanf, which will allow me to return a 32-bit integer. So that's all this does. And it actually prompts the user as well using standard error. So you'll notice that when you use this function, you'll get a prompt to say, please enter a number or something like that. The only reason I did, so that'll be printed to standard error, that message. So the way we check that ground truth error, we'll just see if the line that we expect is in your standard error output. But if you have other stuff in your standard error output, it won't affect anything. So the reason I have that printed out is that at least last semester, when the machine was waiting for input, some students believed that their program was hanging. So that'll be very clear that your program is waiting for input or not waiting for input if you don't see that prompt. So that's what the read instruction does. And I'll go over more today how to actually, how to generate code for that. Other questions? Other questions on the language? Okay, I forgot what I was talking about before I asked that question, but anyway, so let's move on to looking at code generation for variables then. So as we talked about, I guess last week, the way variables work, at least in the way I encourage you to implement it, is variables are going to be associated with memory locations. And in this case, variables are going to be associated with memory locations on the stack. So I'm assuming everybody's more or less familiar with the stack from computer organization and logic, right? Does anybody want to go over stack and heap a little bit at all? Anybody? So, the stack grows down from the top of your memory addresses, at least on the Intel architecture. Your heap grows up. Your code is at the bottom, the near zero, near the zero index memory address. And so it's just different conventions for allocating this whole, memory space that you have available to you as the programmer. So we're going to use stack allocated addresses to represent and store our variable values. The way this works in LLVM is LLVM conveniently has an instruction called alloca, and we can use this instruction to tell LLVM to make space on the stack for our instruction or for our memory address. But you as the compiler writer need to keep track of which memory addresses correspond to which variables. So the way how did we solve that? How does the compiler know which memory addresses correspond to which variables, which symbols in our program? Does anybody remember? Nobody?
Just a symbol table?
Just the symbol table, yeah, the symbol table. The symbol table is this global state that the compiler uses to keep track of which identifiers in your program correspond to which memory locations. So this is how we implement the semantics of these mutable variables that we have in our language. The compiler just treats them as memory addresses and keeps track of which memory address corresponds to which variable name. Our assignment statement here, if you notice our assignment statement, it takes an identifier and sets it equal to the result of an expression. So what that means is we can use this nested structure of context-free grammars to not even, when we're defining how a variable assignment looks, we can just offload all that work of defining what an expression means into this non-terminal for an expression. So that's very convenient because now that we have the expression implemented already, we don't even have to think about how that's implemented anymore. This corresponds to just a recursive function. And we can use the function abstraction to just say, I assume the expression is already written correctly. I know that it returns, well, what does it return? What does expression return in this recursive descent parser? What was that? Yeah, it returns a temporary variable, some LLVM variable. That's how I recommended you design it. So now that we know there's a function called expression that as input, it'll take, the rest of the, it'll take the position in the file, the rest of the characters in the file, and it'll return some temporary variable that is guaranteed, as long as you implement it correctly, it's guaranteed to hold the value of that expression. So remember, the expression doesn't actually return the value of the expression. It returns a variable that at runtime will hold the value of that expression. That's because we're generating code. We're not interpreting this code. We're generating an equivalent version of this code. Okay. So our assignment instruction will just call on expression, assuming that it's already correctly written. And so this is what I like about grammars and recursion is that you can just kind of compose these parsing functions of your grammar and not even have to worry about the entire language all at once. You can just break the language down into pieces make sure each little piece works, and then these functions will compose together. So once you've written the expression correctly, you know that it's going to return a temporary holding the value of that expression. You can just use it as if it's a black box. You don't even have to worry about what its implementation does anymore. And if there's a bug and you find that there's a bug in expression, you can test that in isolation, just test the expression method. So this is the beauty of the function abstraction and the utility of doing recursion and making these recursive functions composable. So the read statement, somebody asked about this already, it's kind of like print in that we call a library function to do the read for us, but the difference is it's taking input. So we have to store that value somewhere. So when you emit the equivalent LLVMIR for read, you not only call the read function, but you have to save the return value of it, and then use that return value to update your variable. And then, of course, we also need to update factor. So factor used to just take either a parenthesized expression or a number constant. Now it can also be a variable. And when we see that, we have to load the value of that. We have to generate code that will load the value of that variable into a new temporary register. Okay, so let's go through each of these new additions to our language and look at what some pseudocode for what this parser should do in order to generate code for it. So in the bottom right here, I've added some pseudocode here. And so just to kind of go through, it's pseudocode. It's not exactly what your code's going to look like. So I just have this function called consume, which means get the next token from the input. I can set, if I don't actually need the value of that token, I just say assert to mean make sure that the next thing in the input is an int. For the declaration, what does the declaration look like? It's just the int token followed by an identifier token followed by a semicolon token. That's all the declaration looks like. And so I assume that I save the value, which is the string value of the identifier, in this identifier variable. Okay, so that's the parsing part of this declaration. And so what do I need to do in order to declare a variable? Well, I first need to make sure that there's no previous definition of that variable. So I kind of assume a symbol table ADT here, abstract data type, that has a contains function that will just check whether the symbol table already contains that value, right? This is just classic dictionary ADT. Put, get, or lookup, and contains. Those are like the main things you have in a dictionary. So I need to check to make sure whether there's a previous definition or not. And if there is, then this is a type error. You have a multiply defined variable that's not permitted in our language. We only want one memory address per variable name. So I've given you example code or example output to show what that error message should look like. It just says something like error multiple definitions for X or something like that. So just follow that pattern of that error message and just make sure that your error output at least has that line somewhere in your error output. And the grader scripts should be updated eventually. I don't know if they're updated yet, but they should be updated eventually to check for that and give you that feedback. Okay, so now that we know that this variable hasn't been defined before, what do we have to do? We have to allocate memory for it and update the symbol table. So to allocate memory, we emit this alloca instruction. And so what does alloca return? Does anybody remember what the allocate function returns? An address. Yeah, good, an address. And in LLVM, its data type is a pointer to, for us, it's I32 is our only type right now. So it's just a pointer to I32. And so the way I propose you handle this, because LLVM is not dealing with real concrete memory addresses, we can store those memory addresses in an LLVM variable. So I recommend in the symbol table just storing that variable in the symbol table. So we make a new temporary variable to hold the address at runtime and emit a new instruction that assigns that new temporary variable to the memory address that's returned by alloca. So again, keep in mind that this is not running the program. This is generating new LLVM code that will be equivalent to our input program. So the equivalent of declaring a variable in simple C is generating LLVM instructions that call alloca and save that in some temporary register. And in order to remember the fact that that temporary register from LLVM has the memory address of our variable, we save that variable name, that register name, in our symbol table. So we map the identifier that we parsed, which is the name of our variable, we map that to the LLVM register name that we just created. So hopefully everybody knows how to make new temporary registers. You can use the same functionality you had before for project 0 and 1. So questions on this? Pretty straightforward, more or less. Yeah.
So the register, would the pointer be 64 bits?
Okay. So this is the difference between what the thing it's pointing to is and what the thing itself is.
Yeah.
So the pointer itself is a memory address. What it's pointing to is an I32-bit number.
Would the register hold the pointer?
Well, the LLVM register. Yes, the LLVM register, or the LLVM temporary variable, holds the pointer value. But LLVM abstracts away the details of what the memory addressing looks like in the hardware. So the type of the register is referring to the type of the thing that it's pointing to. So it's I32 star, which means the type of this temporary value, this temporary register, is pointer to I32. It's like int star in C. It's just like that. So that doesn't tell you anything about the pointer itself. So the pointer itself, might be 64-bit on a 64-bit machine. But the thing it's referring to is a 32-bit number. But yeah, that's a good question. So it's the distinction, this classic distinction between the symbol and the thing that the symbol represents. It's very easy to confuse these two things, even philosophically. It's easy to confuse these. Good question. So other questions? Other questions about this? Okay, so how do we do read? So read is also a fairly simple to parse. There's just 3 tokens. We've got the read token itself, we have the ident token, and we have yet another semicolon at the end of it. So the way we handle read is read assumes that the variable is already declared, that we already know about this variable and we've already allocated stack space for it. So how do we make sure that the variable is indeed actually declared? Or what happens if it's not declared yet? What happens? What should our compiler do?
Not declared, it should throw an error and stop.
Yeah, it should throw an error. The semantics of our language is that you have to declare variables before you use them. You can kind of see why C uses this rule about declaring variables first, because it makes compilation pretty straightforward. Stack allocation typically happens at the beginning of a function. It doesn't have to, but it's just easier to program this way. It's easier to write the compiler this way. You know that every variable is going to have a stack allocation, so make the programmer tell you about all the variables first. So you know all those variables up front, and they'll all be in your symbol table. So yeah, exactly. So if the variable hasn't been declared yet, it's not going to be inside our symbol table. And so I use this little shorthand here, a kind of Perl-esque shorthand or Bash kind of shorthand, to say look up the address, which for us is a LLVM register name. Look up that address in our symbol table, and if it's not found, print out an error. And again, I've given an example of what this error should look like. It'll say something like, X is not declared yet, or something like this. Look in the examples. Yeah.
So in this example, why do we look up the register or the LLVM value to the identifier variable name?
What?
Like in the previous example, we looked up the variable name. It was
Yeah.
Can you do either or whenever you're checking for the symbol table, or?
The symbol table is always keyed. So the symbol table is a dictionary. So it always has a key, which is always the variable name, the simple C variable name. And its value is always the LLVM register that will hold the memory address of that variable at runtime.
So
Well, you use the key to look up. Your goal is to the goal is to map whenever you see a variable in simple C. You want to figure out where its memory address is, and to do that, you keep a table that maps the simple C variable key to the LLVM temporary register that holds the value. And I know I'm using variable a lot, which makes it confusing. They're both variables technically. So it maps the simple C variable to the LLVM register that holds its address. And so you're processing the simple C program. You're just processing that as input and LLVM as output. So wherever you see a simple C variable, that needs to be replaced somehow with the address of that variable in LLVM. So you're always looking up the simple C variable name. Does that make sense?
Yeah.
Makes sense. So I'll show an example. I'll show an example after this as well. Okay, so our language assumes that these variables have been declared first. So we look it up. If it isn't declared, we emit this error. Otherwise, we want to call our read integer function. So we have to emit our read integer, a call to our read integer function, just like it shows in the project 2 description. But read integer returns an I32. It returns a value. And so we need to store that value somewhere. So to do so, we make yet another temporary register, LLVM register, to hold that value. And that is the value we use in our store command to write the value into the memory address. So we emit, so the goal of a read is eventually to have this LLVM store instruction be emitted by the compiler. And so in order for that to work, we need to have a register that holds the value to be stored, and we need to have a register that holds the address that's being stored to. So in order to get the address, the symbol table holds that. And in order to get the value, we call the read integer function. Questions on this? Pretty straightforward? Okay. Oh, yeah, go ahead.
So when you have, so let's say it's like a read X.
Yeah.
You have a variable X that holds the address of a temporary variable to represent that X in the LLVM space.
Yeah.
And then when you read in a number, that number itself will have the temporary variable LLVM.
Yep.
It needs to store.
Yep, exactly, yeah. Yeah, so you need to make a temporary variable to hold the return value of read integer, and then emit an instruction that will take whatever the value of that variable is and put it into whatever the address is. Other questions? Okay, so let's look at assignment. Assignment is somewhat similar. The parser looks like this. We have an identifier followed by an equal sign, followed by an expression. So expression here is a non-terminal, so it could expand to any arbitrary expression, and then followed by a semicolon. So the key difference here is that our expression, based on project 1, the only time expression was used outside of expression itself was for a print statement. And how did the print statement work? You just call the expression parser, and it gives you back a temporary variable or value, depending on how you implemented your parser. But it gives you back some value, either as an LLVM register or as a constant. And because that's already written, all we have to do is write a store instruction that takes the register holding the value of the expression and storing it at our variable's address. Just like we did for read. And just like we do whenever we need to check the memory address for our variable, we do a lookup and get the LLVM register holding the address. So I kind of always call this the address because I want to kind of emphasize that this is an address. But really, in your compiler, it's going to be a LLVM register that holds the address. Make sense? Questions on this? Okay. Oh, yeah.
So the LLVM registers that hold the addresses, that can be the same type, like it can be the same like letters and stuff as if it was any other.
Yeah, you can use any letters you want. You could even use the variable name itself. You could do that. You could do that. I have it just generating temporary registers because I find it easy. You have one function that just generates an endless number of temporary registers.
But it doesn't have to be different than your expression variables, right?
So LLVM is static single assignment form, which means every register can only be assigned once.
Right. But if you increment all your variables,
Yeah.
and you increment for that one, you can still follow that same method that you're incrementing, right? Or
Yeah.
would it have to be different?
Yeah. You can always, you can generate temporary variables the same way you've been generating them. If you always just increment a temporary register, you can always do that. Other questions? Okay, so let's look at factor. Factor is slightly more complicated, but not all that much different. The big difference is that factor is retrieving the value at the address instead of storing it. So all the examples we saw before was storing the variable address. Factor is how we retrieve it. And this makes sense, right? If you have print 1 plus x, you're trying to get the value of x and add it to 1. So the way we translate that to LLVMIR, or the way I'm recommending you do it, is by using a load instruction to get that value out of memory and put it into a temporary register. So I've sort of elided the rest of the factor, but just keep in mind that this is an addition to your current factor function. And it's just a single token in this production for factor. It just is a single identifier. And so all we have to do is look up our memory address, just like we did before. If it's not found in your dictionary, then of course it hasn't been declared and probably hasn't been assigned either. So you just emit an error, and you can look at the example test cases to see what that error should look like. But the difference here is that factor needs to fit into the way we parse and generate code for other factors. So what does factor return? What does factor always return? A number or a temporary register. So depending on how you implemented it, it's either going to be a constant or a temporary register. Well, in this case, can we return a constant for the variable? It's kind of a tricky question.
Define like constant as in
A constant integer rather than a temporary register. So some of you, I realize people implemented this in different ways. So some people returned a constant value whenever they saw a number. Some people immediately put that into a temporary register so that every function would return a temporary register, which is a nice simplification. But in this case, we have a variable. We don't have a constant number. So what can we return? Or can we still return a constant? What's that? Yeah, we can. Well, okay. So what we can do is we can have a load instruction from the address of the variable, and make a new make yet a new temporary register to store that value in. So what is the meaning of a variable in LLVMIR? It means load that value from memory and put it into a temporary register. And my compiler, since my compiler already knows how to parse and generate code for expressions, this just slots right into all the other kinds of factors that we have. Factors always parse, get some temporary register, and return it to its parent. That's what a factor always does. So we can just fit right into that by making a new temporary register and loading the variable's value from that address that we know by looking up in the symbol table. Questions on this? Questions? Yeah.
Yeah, so I guess maybe that's kind of I missed the very beginning of what you were saying about the constants. My factor will return a constant if it or it returns a constant if that's what's been put into expression. So expression returns a string that says 5 on it.
Right.
Will that conflict with the assign?
Well, in another factor allows for parentheses e parenthesis.
Yeah.
So in that case, you may not be able to return an integer constant.
Oh, it's actually a character string.
Oh, it's a character string.
Yeah,
Yeah.
but it says 5, so
Uh,
like T1 or
It depends on the meaning of that. What meaning? What is your API? What does
If
that
my
return value
expression-
mean?
If I called expression, say with print 5,
Mhm.
the expression is just going to go all the way down. It's going to say none of these work, and then it comes back up and it returns a character string that says 5.
Oh, okay, yeah.
And for this one, we're calling expression and setting it equal to, some sort of buffer that we're then storing. That'll still work. Can I use the LLVMIR that says store 5, comma, in the address that I passed it?
Could use a temporary variable.
Well,
Instead of a temp variable, yeah.
a store 5. You mean store 5 here?
No, it'll be in the prior slide, not this one. Yeah, store result. Result's a character string in my code, but for LLVMIR,
Oh, I
it's
see.
print 5.
I think that's okay. Yeah,
Okay.
I think it's okay to put constants in store.
Okay.
I think that's okay.
Yeah.
That's all you're
Yeah,
asking.
okay, that's good.
So factor will sometimes have to return a temporary register rather than
Yes,
a constant.
So it'll have to depend on a number.
Right.
or a
It
temporary.
just depends on the meaning. This is like what programming is all about. It's defining what your abstraction is. So if factor returns a character string, that could mean many things. You have to define what that means in your program. So does it mean an integer constant, but the ASCII version of it, so that it's easy to print out as LLVMIR?
Yeah.
Is it a complete LLVM temporary register name? Pound T something. But this is what software engineering is all about: is defining what your abstractions are, but being extremely mechanically clear about what they are, so that when you have the other pieces of your program will just work seamlessly with your other abstractions. So you have this factor abstraction. This is why commenting is kind of useful. You don't have to comment every line necessarily. I used to hear that it should be 2 lines of comments for every line of code, which sometimes can be, I don't know if that's actually good advice, but each function should at least be defined in prose, ideally. What are its inputs and what are its outputs, and what is the meaning of those outputs? And ideally defined for all possible inputs and all possible outputs, even if it's just that's an error if it's less than 0. That's fine, but as long as you kind of fully define what the function does, and also consider its side effects. So does it read from input? Does it set some global variable? I know a lot of students are now terrified of globals, right? You've been have that beaten into you to never use globals. Well, all rules have some exceptions.
This project is an
Variables
exception.
in this project.
What's that?
I've got about 15 global variables.
Yeah, so in certain applications, global variables are fine, I should say, but you should, it's always you can always go too far in a rule if you're sort of fundamentalist about the rule and always bend over backwards, and you can actually have a worse code if you try to follow all rules dogmatically. But anyway, if you have such global behavior, that should at least be in your specification of the function. You should at least admit it to everyone so that when they use your function, they'll be like, well, okay, here's what I can expect. I can expect something to break because I have some global value being used. But there are some languages where you don't really have global values. Like Java has objects. There's no real global values. They're all names-based. Or pure functional languages that don't allow side effects. Which, yeah, if you're taking programming languages, you'll learn about Haskell. Anyway, so, question?
Sort of. I was actually, you were on the global thing.
Yeah.
Is our sim table going to be a global thing?
Yeah, you can make the sim table global.
Oh, I think
You can make
Otherwise,
the sim table global.
we have to pass it through.
Yeah, it's just the difference between always passing this value and
Okay. I was just curious.
Yeah, so the symbol table is going to be this sort of persistent state over, and even in theoretical computer science, there's this notion of environment that gets passed around, but it's kind of a persistent state.
Is that
And
what you recommend?
yeah, you can just have it global. It's okay. For this particular application, it's okay to have a
Yes.
global. Keep that rule in mind. That is a very good rule to not rely on globals, to try to define things functionally without so many side effects and without trying, because it just makes it easy to manage your state of your program. But for this, it's okay. The symbol table is a global piece of state that your entire compiler needs, and that is sort of updated as side effects of each of these calls. It's okay for this application, just this application.
Okay.
Yeah.
Would you say, is it dangerous to kind of say, if you're passing in something to every function, should you just make it global? Or is that kind of dangerous thinking?
I can't, we'd have to prove that is true. I don't know if that's true.
Okay.
I'm not sure that that's true. Yeah, I wouldn't say that. I'd say if you're writing a C program and you're writing a compiler, you may have global values. If you're writing in C and using a compiler. If you have C++ or some object orientation, you can make that what would be global, you can at least encapsulate it in your object. Maybe you have a parsing object, and that parsing object has a simple table. Yeah, and it's private. Yeah, so at least you sort of compartmentalize that state.
The global, it just means that it's susceptible to being tampered with.
Yeah.
Yeah.
And it's easy to lose track of the effects on your state. Yeah.
The kind of just a curious question. Are most
Yeah.
compilers written in C or is it just
Are most, so I don't know about all compilers. Some of the most popular compilers, like GCC, I believe is written in C. Clang, the one that we're using for class, is C++. And I imagine, I haven't tried to look at the GCC code in a while, but I imagine you'd have some very C-like implementation in there. Yeah. And actually some tools for generating compilers, like parser, there are parser generators and regular expression generators. If you remember that subset construction algorithm for going from NFA to DFA, that's part of that can be part of a regular expression compiler, something that'll take a regular expression and turn it into code for you automatically. And those, just by default, if you use the C versions, will just sort of give you global state, global variables. But anyway, kind of a digression. But I don't know about all compilers. I don't know. They're all written in C. A lot of the big ones are C and C++. Yeah.
I'm actually going to focus on this now.
Okay.
Sorry, we don't want to tangent.
Sure.
What if that variable hasn't been initialized yet?
That's a really good question. Yeah. So what if this is a really good question. Same in C. If I declare a variable int x and I print that variable, what happens?
You just get some random number.
You get garbage. So what does that mean to have garbage? Is that like the semantics of your language is return something random?
Whatever bits were on or off in that spot that X is pointing to, that's just going to be what X would print.
So this is kind of a case of where, like, the lack of language specification kind of bleeds through when you actually implement it, when you actually turn it into machine code. So I think the C specification, it calls this undefined behavior. Like the C designers are like, certain cases we're just kind of throw our hands up and say, we don't define what that means in our language. That's kind of bad for users because most compilers will not stop you, right? Some compilers will warn you for uninitialized variable usage. Yeah.
If you have an uninitialized struct,
Yeah.
then it won't let you compile.
It won't let you compile.
Yeah.
Okay. Yeah, and it depends on. Yeah, I don't know what the state of all the warnings are now. You can even tell you can even tell GCC to say, if there's a warning, turn it into a compiler error. You can just, because it's a choice, right? It's a choice by the compiler about whether that is a warning or an error. That's a human choice. There's nothing written in law that undefined behavior should be an error. But and this kind of is also kind of related to type checking. For C, we can kind of undermine the type system, and the compiler won't care. It's sort of built into the language that you're allowed to do this, because they need to do, you need to do pointer arithmetic for very low-level programming. So C compilers don't restrict it. Other high-level languages will not permit you to do that. Like Java won't even allow you to touch pointers explicitly. So this is really kind of in the border between language design rather than what's right or wrong, at least in my opinion. Maybe I'm a compiler relativist or something, but yeah, it's sort of hard to say what's right or wrong. It's sort of an engineering choice at that point, like what's the best tool for the job. But there are modern languages where, like Rust, for instance, that'll do its static type checker is much, much stronger than C's, and it can provide guarantees like this piece of memory is only referenced by a single variable at a time, which is something that C, of course, does not give you. So if you free a value, you call malloc and you free it, there may be other things pointing to that, and there are lots of vulnerabilities, security vulnerabilities. There was actually a Linux vulnerability where, because of this freed memory, one part of the kernel didn't know it was freed, and another part thought it was still there. And so somebody was able to actually get root access on the machine because of this dangling pointer to what memory, the memory that the machine thought was free, that the kernel thought was free. Yeah, but so the problem is these kinds of guarantees, so that the type checking guarantees that I showed you are like, people have known this algorithm for a long time, type checking algorithm. But for things like, is there a null pointer error here? It's a much harder question. In fact, it's impossible to know exactly in all cases because of Turing's undecidability problem.
So,
But yeah.
if we come across, like, we just throw an error? Or would you
Yeah, you could. So in the what I've given you here, I don't say anything about it. I don't say it has to be an error. So it'll work like C's undefined behavior, where you get garbage values. So this is kind of like what the undefined behavior is, sort of an escape. It'll say like all of the rest of your computation is like, could be anything at that point. And even compilers will even exploit this in order to do optimizations. Like knowing that is undefined behavior, the compiler may make some choices about what to do in those cases. So for instance, maybe it, for instance, it won't zero allocate the memory. It'll just leave it to be garbage. And then it's sort of your fault as the programmer for using an uninitialized variable. Oh, that's a good question, though. That's a good question. So another little tricky question is, to getting back to this example, do we always have to return an LLVM register for our variable? Or could we return, say, an integer constant? A little bit of a trickier question.
It depends what they...
Somebody said what, right? So if I have like a program, okay, well this program is not going to be a good example. So in this case, would I be able to return, so for X, normally the kind of default that I've shown you is return the LLVM register that holds the memory address. In this case, is there a way I could return, say, an integer constant instead? Yeah.
No, not with the way that it's being implemented currently.
Yeah, not with the way it's being implemented here. What if instead I said something like x equals 10? What do you think? Yeah.
No.
No? So you don't think you could return 10 here?
You would have to store it somewhere.
Okay, but you could do it, right?
I suppose.
If you really wanted to.
If you really wanted to. Well, modern compilers do this. Modern compilers will actually do this. Shall I show an example of this?
Yeah.
Let me show an example of this. Okay. So this is something I'll get to a little more at near the end of the semester, how this actually works in a compiler. So let's make a little test program here. Let's call it constant. And hopefully I'm not lying. Let's do x times 10. So we know we should get 30, right? It should be print 30. Let's make sure this actually works. Okay, I didn't include standard I/O, so it's complaining. But that's okay. All right, so let's compile this with no optimization. So intuitively, I think I've shown a lot of optimization kind of intuitively lately. And we'll talk about it more at the end of the semester. That is annoying me, but okay. So here's the source code. Do we have a multiplication here? Let's see. We've got adds. Ooh. Okay, I confused myself. This is doing a little magic. I thought I turned optimization off. Where's the call to print? Is the call to print? Let's move 0 into here.
Did it just add 10 3 times?
I think it might have actually.
They added what 3 times?
Did it just add 10 3 times?
Maybe, but where's 10?
Oh, well, I don't know, but I'm just
Well, it's
thinking,
just like, add left twice.
Yeah, it seems like it already kind of optimized it away. Ooh. I probably should have prepared this. me try a different number. That's less obvious. So small numbers, maybe it's doing something wacky with small numbers, where it's able to do that. Okay, so we got rid of those. So it was doing something funky with small numbers. Probably gains like, a few clock cycles or something. So here we can see we see the actual multiplication now. So there's 343. Here's the multiplication, and then it sets up the parameters and calls print. Okay, so that's without any optimization. Let's turn optimization all the way up to 3. And you can see here, the compiler actually bothers to do the multiplication instead of doing a load and a store. So why would this be beneficial? Why would we even want to do this? Well, it still has the local value variable.
Cycle time?
Actually, no, I think it did remove the variable. So yeah, it would save space. It would save stack space. Wait, did it? Okay, I'm not sure if this is, so it's still using stack space. I'm not sure if this is the actual variable or not, but yeah.
Saves computation at runtime.
Yeah, saves computation at runtime. Why?
Because you don't have to do the multiplication, it's already been done for you.
Yeah, you don't have to do the multiplication.
That it's just a constant, so.
It's just a constant. But even more importantly, so multiplication is one thing, but stores and loads to RAM. So if you remember from computer logic and organization, this hierarchy of memory, registers are the fastest.
Yeah.
Then you have L1, L1 cache. I'm not an architecture guy. All the levels of cache, and then RAM is the slowest. Right. So you can do tons of other arithmetic operations in the time it takes to a single load. Yeah. So if you're always going out to memory, then that's bad for performance. So doing this kind of what's called constant folding is one of the first optimizations that compilers do, or ever did in history. It's one of the earliest ones. And we'll talk about that a little bit, how that actually works near the end of the semester. But yeah, I just wanted to kind of ask a tricky question. Do you always have to return a register and do a load, or can you do something better? And it turns out you can if you know it's a constant. And this is also related to type checking. You have to prove, the compiler technically has to prove that is a constant value for any input in the program. So that's why if we had read here, there's no way outside of the program that the compiler can guarantee that will always be a constant. Maybe if you gave it some input specification, the compiler could do that. Maybe if you said, okay, x is always going to be 10, or x is always going to be divisible by 2, for instance, then the compiler could provide some stronger guarantees about these optimizations and the behavior of the program, and even maybe guarantee that there's no null pointer errors, for instance. Okay, questions on this? This is getting maybe a little ahead to the optimization point. What's that?
Yeah,
how you implement that? Well, just like your classmate said, you already have a symbol table. So in addition to the register that holds the value, you can also store what you think the constant value is for that. So when we see x equals 10, we have another entry in our symbol table that says 10, and then, once we have conditionals, it's going to be a little bit more complicated. But in this version of the language, there's no conditionals. So x will always be if you're not reading it in, x will always be a constant. And so you can just keep track of that.
For us, since we're storing it as character arrays instead, would that still behave that way if I were to add that field to?
You'd have to do the conversion from ASCII representation of the number to integer representation, or you'd have to write your own arithmetic in ASCII. That would be rough. Yeah, you can just use the compiler's language itself to do the computation. Okay. Questions on this? That was a little tangent on maybe a more advanced portion of compilers, and we'll get to that a little bit at the end of the semester. Okay, so I just wanted to finish this up with an example. Just walk through an example of generating code, and just walk through it very carefully and very slowly, and feel free to stop and ask questions if you don't understand something. So this is hopefully the same program that I've got here, more or less. 2 integers are declared. Let's see if this works here. 2 integers are declared, and we've got a read, and then our assignment to an expression. So let's walk through each thing. We're going to take those code generation routines that I showed you and walk through each part of this tree. So one thing that I didn't really get to much recursion a couple weeks ago, and I only covered it a little bit when we talked about factorial. But there's this strong relationship between trees, recursion, and context-free grammars. They're really all kind of representing the same computational concept. With recursion, we see with the parser how it is like a grammar. A grammar is really just this arbitrarily long recursive expression of some language, and that's exactly what recursion is. You can actually write a parser that just is recursive descent. And the trees is related to recursion in that each node of the tree is like a function call, and each child node is like the functions that were called in the body of that recursive function. So when we think about this, so this is the parse tree, but we can think about this also as a trace of how your recursive descent parser operates. And so I'm going to add in the code generation calls as well. And the same way you can do with the type checker. You can add in the type checker or any kind of processing of this language. You can think of it as actions or extra nodes on the parse tree. So to make this a little clearer, so let's start parsing this. So this is of course going to be a post-order traversal like we've been doing for type checking. So we start at the program, the prog at the top, and the first thing we see is a declaration. So I've elided the whole parse tree here just to make this a little easier to read. And in our code generation, remember that we parsed the declaration first, and then the next thing we did was what? What was the next thing we did in code generation for a declaration? Does anybody remember? What's the first thing we do? Or what's one thing we have to do when we're generating code for the declaration? Add to the symbol table, yeah. But first, to make sure that value isn't in that already, we have to do a lookup. So we do our lookup, we do our error checking, and then we add that value to the symbol table. So I think I called it put. And I'm just going to say we make some new temporary register. And what else do we have to do? What else do we have to do for a new variable?
Emit the result.
Emit? Well, what do we emit? Or what does our equivalent LLVM program do when we see a new variable? Where does it get stored?
Oh. Alloc.
Alloc, yeah, exactly. So we have to emit an alloca instruction. I guess more specifically, it's emit T1. Well, I'll put the actual output down here, but we have to emit an alloca instruction. So in my output down here, T1 is my new variable, and it gets the result of the alloca instruction. So you can think of this red line here is like another node on our parse tree. So each recursive call in your parsing in your parser, in the code for your parser, is like a node on this tree. And it's like recursively expanding this tree each time you do a new function call. You can think of, so instead of thinking of the recursive function as calling itself, think of it as calling a new version of itself, a new copy of itself. And that's a new child node in the tree. So after we parse int x semicolon, we then call the code generation routines right after that. And that fits right here on our parse tree. With me so far? Questions on this? Okay, so we're finished with this declaration. We go back to the program root node, and we go to our second declaration. So what happens in our second declaration? Oops, I forgot to put this in the table. But yeah, I think I already heard it. It's the same thing. It's the same thing, but for y. So I'm just going to say ditto. Ditto for y. And we end up with a new alloca instruction and a new symbol table entry. Okay, what about for the read statement? Does anybody remember what we need to do for read? We need to look it up, sure. We need to look up x,
Make sure we don't have an error.
and that's gonna give us T1. Yeah, make sure there's no error. It's gonna give us the T1 register. And then what do we need? What gets emitted?
Store.
This-
There's gonna be a store. There's gonna be a store.
The read integer.
And the function that we have to emit the function call to read the integer. Good. So we emit the call. I'm just going to say emit call for brevity here. Well, I'll say emit read integer. So we emit the read integer call, and we emit the store. So I'm going to kind of skip over you can look at the slides for the actual code for this. So we're going to call read integer, put it in a new temporary variable, and then do our store. And we're storing, which way does this go? I think it goes T3 to T1. So this is our X here. Let me put this in another color. So this is X's address. All right, with me so far? Questions? Questions on this? So you can just think of these as extra nodes in our tree. Okay, so now we're in our assignment statement. Right, so our assignment statement, at least, so if we look at the code for this, so this is a little bit more involved. At least the way I've written it. Now, the order, you can sort of change the order if you like. The way I've written it is that the lookup happens after we process the expression, but you could certainly do that immediately to quickly have the error, but it doesn't really matter. You can put that wherever you like. If you have an error, then the program behavior is undefined anyway. So we can hold off looking up this y for now. So for now, we'll just hold off on that y. And now we need to call the expression function. So now it's just exactly what you did for project 1. It's the exact same behavior. But I'll walk through it anyway. So we do this post-order traversal. It brings us to the factor of 1. And depending on how you designed your parser, this will return either the value or a temporary register. And this will be passed to the expression. And based on the code generation routine I gave to you last for project 1, it'll pass the left-hand side of the plus to E prime. And then E prime, as we did before, first has to find the right-hand side. So the right-hand side is eventually the factor that has X. So now we need to do our load from memory. So what does this look like? What does the code generation code look like for this? What do we have to do first?
Check if that variable's in our...
Check if it actually exists. So we do our lookup. Our symbol table in this case tells us yes, it's at T1. What do we need? How do we,
We have to load X's value into another temp value.
Right, exactly. We have to load it into another temporary value. So we're going to emit a load. And so look at the slides for the actual pseudocode for this. It'll make a new temporary variable and do a load from where? What variable holds the address of X?
T1.
Good, T1. T1 holds the address. Okay, so now this, just like before, this T1 is what gets passed up to E prime. E prime has its own emit for, I'm just going to say 1 plus T, oh, this is not T1, sorry, this is T4. Has its own emit for T4. That becomes a new address. That becomes a new temporary variable T5. And we do the same thing for this constant. So I won't go through the whole thing for the sake of time, but this emit will eventually be emit T, oops, did I mess something up?
Yeah, 'cause
I did mess something up.
multiplying and then
Yes, you're right. Did I mess this tree up? I did mess this tree up, right? What did I do wrong? So we met. Oh, right.
Oh, yeah, we missed the
Sorry.
prime. Well, FT prime, yeah.
So, sorry. So that I jumped the gun here. So
The rest of it's pretty simple.
okay.
That middle T, you just need to do a T prime jump. The rest of it, who cares?
You mean here?
No, one over to the left.
A T.
The one that was on X.
Yeah, T goes to FT prime. That's what he's saying.
Oh. Okay. T goes to F. Oh, why am I confusing myself here? Yeah, I messed up because this E prime does not have a star underneath. So I am going to, for the sake of time, I'm just going to remove this tree to make this easy. So it's just 1 plus X because I kind of botched that tree. Okay, so this is going to be just null string. That'll solve my problem. Okay, and so now, the point of this was not to go through the expression again, which I obviously messed up doing. So we get T4 being passed back up to that's our final temporary variable that holds the result of this expression. Okay, so now we have the real part that I wanted to get to, which was how do we emit the equivalent code for assigning the expression to y. So what's the first thing we need to do? Oh, I forgot to do I forgot to do the actual arithmetic. Sorry. So there's going to be the actual arithmetic instruction here, which I'm just going to say 1 plus whatever it was, T4. So this is going to be emit the add. Okay, sorry. So what's the first thing we need to do when we emit code for the store? We need to look it up in memory, or look it up in the symbol table. So look up y, which is the value we're going to store to. That gives us T2. And then how do we store a value into memory in LLVM? Just store, the store instruction. So then we have to emit our store. And I've run out of space, unfortunately. So then we're just going to store our new temporary variable T5 into T2, the address for y. So questions on this? So sorry about it. Sorry about the mistakes. That was kind of sloppy. But questions on this? Questions on the variable stuff? Nothing. All good? All makes sense? Other questions on variables? Pretty straightforward, right? Unless you're doing the expression tree like I was doing and messing it up. So one other thing I'd like to show is that, so I realized that I could have made this a little easier for you for doing the expression parsing and for showing the trees for expression parsing by showing this little optimization to the grammar. So this is not really a context-free grammar anymore. This is a different kind of grammar. But in order to avoid this whole, passing, the parent has to pass to the child, right? The E here, E has to pass to E prime in this expression tree, which is kind of annoying that E has to pass the left side of the operand to E prime. Kind of breaks the structure of what we think of as an expression tree, where the root is the operation and the children are the values. So we can recover something like that in our right recursive version of the parser by substituting this E prime back into E. Now that can't really be done in a context-free grammar, the Chomsky normal form version of it anyway. But I can sort of use this other syntax that actually some parsing, like the ANTLR parser generator uses, where you can sort of combine regular expressions with the context-free grammars and get something that looks like this. So all I've done is taken E prime and substituted it back into E. And so what I get is T is followed by plus T 0 or more times. If you were to like sit down and work through it, I think it's equivalent. I just thought of this today, so I might have made a mistake, but I'm pretty sure this is equivalent. Because what are your three options? They're either, so it doesn't map exactly, but it's either like plus T E prime minus T E prime, or epsilon. So the 0 or more captures epsilon, and the plus T in star captures the fact that this is right recursive. So it's kind of like tail recursion optimization. We're taking this tail recursion and turning it into a loop. So the way that can be implemented in pseudocode is to just read in the left term and then have a while loop that keeps checking whether the next token is plus or minus. So that's what we're doing anyway when we call E prime. So we could just put this in a loop that says while the next token is plus or minus, then consume the operator, consume the right-hand side, and then generate the code for that operation. And to make sure that the new left operand is updated, we take whatever that result from generating the arithmetic operation and make it our new left operand, and then loop again. And I'm pretty sure this is equivalent to the recursive version, where you're passing the left value down to E prime repeatedly and then passing the result back up to its parent. So sorry for not telling you this earlier. This probably would have made your parser a little bit simpler. But you can rewrite your parser in this way. And then the parse tree also looks a little simpler too. So we don't have these E primes anymore. The E can just be T plus T plus T plus T. Just have many children. So it's no longer a binary expression tree, and it's no longer Chomsky normal form. But if you want to do this, if you want to up to you. If you're rewriting it, or if you tried to do the infix to postfix thing, you might want to do this, because the infix to postfix might actually make the code generation tricky. I don't know. Maybe not. I don't know. Maybe that'll be fine. So questions on this? Questions on code generation for variables? Questions on this little hack? Nothing? Okay. All right, so let's end it a little early, and have a good night.